Okay, so this video, I'm actually going to start something new and see how it is received if you find it helpful. So what I'm going to do is, this is a review for a test that I got from my physics teacher for chapters 18, 19, and 20 in the Giancoli physics book. Well, that's the author, Giancoli. It's the 7th edition. So if you have, and I'll put more information about the actual title of the physics book in the description. But if you are having maybe a quiz on these chapters, or like I am, a test, then these questions are questions that you would probably see on a test, since my professor has written them up or pulled them from a test bank. And so hopefully this will be helpful to you. All right, so let's go ahead and get started here. So the very first one, there's going to be 10 questions that we go over. The first one says, find the equivalent capacitance of the circuit below. So the very first thing that we do when we're analyzing a circuit for resistance or capacitors, and I'll try not to, sometimes I say, resistors instead of capacitors, but right now we're talking about capacitors. So if I say resistance instead of capacitance, forgive me, I'm talking about capacitance. Okay, I'll try to be clear though. The first thing you have to do is, if you were doing this on a test, you would have to redraw your circuit every single time. So let's make this a little bit smaller, since we're going to have to do that. Okay, so the very first thing we're going to do is we're going to work with this part, and we're going to combine this and make it into a more easily or more manageable circuit. Oops, I don't want to do that. It's a little too much of an erase there. Okay, we'll just leave it like that. Okay, so for this, when you're adding capacitors in parallel, you just add them linearly, which is the opposite of how we add resistors in parallel. And so this is all microfarads, they're all the same unit, so this is going to be 12 microfarads. And then what we're going to do is we're going to redraw our circuit. So what we'll do is we'll number these. This will be 1. This will be 2. So what we're going to do is we're going to take these 3 that we just drew. Actually, you know what? Do like this. There we go. And we're going to take those 3 and we're going to turn them into just 1. So we have combined that capacitance to where it is now just 1 equivalent capacitor of 12 microfarads. Well, then the next thing we're going to do is we're going to combine these 2 together. Now these 2 are in series. And when you add capacitors in series, you take the reciprocal of the sum of the reciprocals. Let's put this in our calculator. And if at any time you want to try these questions, feel free to try them and then check your answer so you get comfortable with your own calculator and your own calculations. And so I get an answer of 4 microfarads that is going to be an equivalent for these capacitors that we just drew. So now I'm going to bring this over here. Well, maybe like right here. It's getting a little crowded. Okay. So now we're going to call this one, we'll say number, that one's not pointy. Okay, 3. And then we'll take these we're going to combine these two now, which is what we just did, into just one capacitor. Okay. And this one has a equivalent capacitance of 4 microfarads. Well, now we need to, our goal is to get everybody in, in a series. So we're going to condense down. So now we're going to tackle this guy right here. And they're in parallel, so we're going to add them linearly. Remember, we're in units of microfarads. So we redraw our circuit. All right. We're getting smaller and smaller here. Okay, 4. And you're going to have my drawing, which I won't hopefully be doing a lot of on this one because it's not near as pretty as the ones that are just pictures. Okay, so this is 9 microfarads. Now we're going to combine these two right here. And they are in series. Ooh. Let's see what we can do. I hope this stays on my camera screen. So we're going to say 1/9 plus 1/3 to the -1. Let's add those up. And we get 2.25 microfarads is our equivalent capacitance for these two capacitors. So let's go ahead and redraw our circuit, which is getting really, really tiny. Okay. Call him number 5. We're at. Okay. And so we took those two and we've combined them into just one, which we can leave over there. And his value is going to be, what did we say? 2.25 microfarads. Okay, so now you see we've gone from 1, 2, 3, 4, 5 capacitors, and now we just have 2. So now we're going to combine these two right here, which we can do right here. And these are in parallel, so we're just going to add them linearly. And that's going to give us 6.25 microfarads. And what that would look like is if we took this, oops, oh man. Okay, that works, maybe. Okay. Now we would only have one capacitor with a capacitance that is equivalent to all of those capacitors. And now we know the value that would be. It would be 6.25 microfarads. Okay, so that's how you find equivalent capacitance. So the big thing is just to make sure that you redraw your circuit every single time. And you make sure that you're following the rules for adding the capacitances. All right, and then for this one here, it says a car battery. Let me erase this right here. A car battery runs the vehicle's electric starter motor, which starts the engine by supplying a large current. Then the alternator takes over supplying the vehicle with power and charging the battery. So if you didn't know, now you know. What is the average current involved when a battery sets in motion 720 coulombs of charge in 4 seconds while starting an engine? How long does it take 1 coulomb of charge to flow from the battery? Okay, so for this one, I'm going to use the guess method, which is something that I use for solving physics problems. It's very helpful to organize your information, and it also is really helpful because your professors will often give you partial credit if you don't get the answer right, if your process was correct. All right, so let's look at G. What are we given? So here we're given, if we look at the problem, it says the battery is set in motion 720 coulombs of charge in 4 seconds. So we're given 720 coulombs per 4 seconds. And, okay, then we'll go to our unknowns. So it says, what is the average current? So I average involved. And then it says how long. So we know when it says how long, that it's talking about time. So the time to take 1 coulomb of charge to flow from the battery. All right, so this is an important part. This is our equation. So if you have an equation sheet that you're allowed to use, I highly recommend making sure that you spend a good quality of time putting that together while doing problems, while watching videos, while being in class. Make note of all of the equations that are given to you and that you find that are helpful. Okay, so some equations that we can use is I know that current, which is represented by I, is equal to charge divided by time, which you see we already had up here. And then it says how long does the time, how much time does it take for 1 coulomb of this specific charge to flow from the battery. So if we rearrange that, it would be T equals Q divided by I. All right, so now into our substitute and solve, which we don't need to do a big solve, so we'll just put these together. So what we can do here is to find our average current, we say 720 coulombs divided by 4 seconds, and that's going to give us what our current is, which we're going to need for the next part of our problem. So 720 divided by 4 is 180. So 180 amps. And now we want to know how long does it take for 1 coulomb of charge to flow. So, we'll say T equals 1 coulomb divided by our 180 amps. And let's see. It's going to take 5.56 times 10 to the minus 3 seconds. All right, so that was pretty manageable, right? And if you look at this, you can be like, oh my goodness, what do I do? But if you have that equation sheet and it's organized, it's going to be super helpful and take the extra out of test. All right, so let's see what else we got here. It says, given a battery has a 12-volt EMF and an internal resistance of 0.1 ohms, calculate its terminal voltage when connected to a 10-ohm resistor. Okay, so let's first, since we're not given a picture for this, let's draw a picture. So, told you I wouldn't have to draw. I didn't mean to lie. Oh, okay. So, we have a 12-volt EMF, which we'll put right here. And then we have an internal resistance, so like a little bit right there. And it's connected to a 10 ohm resistor. So we'll say right here 0.1, that's supposed to be in ohms, and 10 ohm resistor. All right, and so whenever you're given a problem like this, make sure you can draw a picture, because if you can't see the problem, you can't solve the problem. Okay. Oh. So we'll put this as our givens. And then it's saying, given a battery has a 12 volt EMF, so we know that, we wrote that down, internal resistance of 0.1 ohms, calculate terminal voltage. So let's look at what else we don't know. We don't know terminal voltage, but we also don't know our current, right? We don't know our equivalent resistance. And I think that's all that we don't know, but let's see. Okay, so we know that terminal voltage is equal to EMF minus current times internal resistance. A little r is internal resistance, and a big R is going to be external resistance. Just a little side note. Okay. And, all right, let's see here. We know that I equals EMF divided by R total, so, or R equivalent. Now, how do we find our equivalent resistance? Well, if we look here, all we have is this in series, and when you have resistors in series, you can just add them like this linearly. So we have 10 ohms plus 0.1 ohms equals 10.1 ohms. And that's going to be our total for this circuit. And so we can find everything else now that we know that. So let's go ahead and substitute and solve. And so let's find our I, so that way we can plug that in. So we have I equals EMF, which we know is 12 volts, divided by R total, which we now know is 10.1 ohms. So let's put that in our calculator and see what we get. So we get 1.188 repeating, and actually, because this is such a easy thing to put in to your calculator, you know, and it goes on forever and ever, then I would just go ahead and plug this right in for this. So let's go ahead and do that instead of having a repeating decimal, just to be as exact as possible. We'll say terminal voltage equals EMF, which is 12, minus 12 volts divided by 10.1 ohms times our internal resistance, which we know is 0.1 ohms. Let's see what that equals. So we'll have 12 minus that times 0.1, and we get that our terminal voltage is 11.88 volts. And that's how you solve that problem. All right, so let's look at this next one. It says, calculate the equivalent resistance of the circuit shown. And what is the power dissipated by the 5 ohm resistor? All right, well, we're going to work this like we did our capacitance problem, and we're going to redraw our circuit, which iPad makes super doable. All right, so call this number 1. So the very first thing we're going to do is we're going to combine these two guys right here. And these resistors, when they are in series, you add them linearly. So we have 6 ohms. And so we are now going to redraw our circuit with that new equivalent resistance in there. Oop. Call this number 2. And let's take this and turn that into just one resistor of an equivalent resistance of 6 ohms. All right, so now what we need to do is combine these two guys, which is 3 ohms. So we will redraw our circuit. Call him number 3. Okay. So now we have a 6 ohm resistor and a 3 ohm resistor in parallel together, and so we'll deal with those. Now when you add resistors in parallel, you take the inverse, and then you take the inverse of the inverses. All right. So we have all right, so this is going to be 2 ohms. So we will redraw our circuit. You see, like, it looked, it's a pretty big circuit at first. And now we're getting down to something really manageable. So now this is 2 ohm resistor. And now we have these guys in series. Let me do that in red. And since they're in series, we can just add them linearly. So we have 2 plus 4 ohms, which equals 6 ohms. And we're going to redraw the circuit. And this time, you see we've gone from all of these down to one equivalent resistor, which is going to be just 6 ohms. Oops, it's not coming off. Oh. And then that is your equivalent resistance. Well, then it says, what is the power dissipated by the 5 ohm resistor? Okay, let me move this guy down some. Whoop. Okay, then we're gonna have to end up moving everybody down some. Okay. So power dissipated by the 5 ohm resistor. Well, we know that power dissipated, the equation for that is I squared times our total resistance, equivalent resistance. Well, we know equivalent resistance now is 6 ohms, but we don't know our current. So if we take this circuit here, move it down, and take a look at it, we can go ahead and we can draw some current. Now, I like to start at junctions. So we have 2 junctions right here. We have a junction right here and a junction right here. So we can have one current going around this way. And then we can have another current going around this way. And both of those currents, we'll call this one I1, and we'll call this one I2. And we know, because of Kirchhoff's laws that we'll end up going over in the next problem, that the sum of the currents going into a junction equal the sum of the currents coming out of a junction. So this is, we can call this one I3, but we won't need that one, because what we're concerned with is using the loop law, which we can apply for this closed loop here to find our current. So if we know that going around, we'll start right here with our loop, and we'll go through this 2 ohm resistor. Let me take that off. Since our current is flowing in the same direction as our loop is pointing, we're going to be subtracting this, and this is going to be I2 times 2. Oops, subtract. And then we're going to keep going around, and we're going to hit our 1 ohm resistor, which is going the same direction as our loop. Our current is going the same direction, so we're going to subtract minus I2 times 1. And then as we continue to go around our closed loop here, we're going to hit a 1 ohm resistor. That now our current is going in the opposite direction of our loop, and so we're going to add the voltage here, which is going to be plus I1 times 1. And we have the same situation with our 5 ohm resistor, where our current is flowing in the opposite direction of our loop, so we will add it. So we plus I1 times 5. And then we keep going, and we have now finished our loop. So sum of all the voltages equals 0, which is that is what this is. Voltage equals I times R, and that's what we have here. We have I times R, and so on. Okay, so now let's put some things together. We have negative I2, and then we're going to put the 2 and the 1 together to equal 3. And then we have plus these 2 I1s plus the 5 and the 1 equals 6 equals 0. Well, remember, we're trying to look for the power dissipated, which means we need a current, but we need the current that's going through the 5 ohm resistor. They didn't ask for these other ones. So because of that, we need to solve in terms of I1, because that's what we're looking for, is I1. So we're going to have I1 equals I2, well, I guess I could leave that there, 6 times 3 divided by 6, so we have I1 equals I2 1/2. And we know that the total current flowing through this is going to be equal to the EMF divided by our total resistance. And so we know that's 12 volts divided by what we just found, which was 6 ohms. So we know that our total current is 2 amps. And we also know from our picture that the sum of the currents entering the junction must equal the sum of the current exiting the junction. And because of conservation of energy, and that's current, it's not exempt from that. It is energy. It is made up of, from what we understand so far, moving charges. And so those charges are considered to be matter and therefore subject to the laws of conservation of energy. So we have 2 amps here is the total amount that these must equal, which is going to be our terminal current. And so we know that I1 plus I2 equals 2. And so what we'll do is, actually, I think that it's better to solve for it in terms of I2. So that way we can put and solve for I1 in here. So let's solve for I2 over here. Let's go negative I2 3 equals, we'll have negative I1 over 6. And then we'll divide by negative 3, so now we know that I2 equals twice I1. All right, so what we'll do is we'll plug that in here. So we have 1 I1, this one will stay the same, there's an invisible 1 right there. All right, and now for this I2, we'll sub in 2 times I1 because that is what we solve for. And then we know that they have to sum to 2. So what we'll do then is we have 3 times I1 equals 2 amps. Well, this just should be amps. And then we divide by 3 on both sides. And we get that I1 is equal to 2/3 amps. So this is the current that is flowing through this 5 ohm resistor. And so now that we have found the current, we can plug that in up here. So we have P equals 2/3 amps squared. And then even though we know that this is asking for equivalent resistance, we have to be careful because we only want to know the power dissipated over the 5 ohm resistor. So we're only going to put in 5 ohms for this one. And then that'll give us 4 ninths times 5, which equals 20 ninths, which when you put in your calculator is approximately 2.22 watts. This is a little messy, so I'll go up here and say 2.22 watts. And that's what you should get for that one. Okay, so what did we do here? We went ahead and we calculated the equivalent resistance, and then we looked at the fact that we had this equation, which was power dissipated. Another question that I found for that one was, let me see. Oh, it was a current limit. It said, what is the current limit across the resistor? This is the same thing. This is the same equation that you would use for that. So power dissipated or current limit is another way you could see a question worded that you would use that equation for. Just FYI. So we looked at this and we realized, oh my goodness, we need the current. So what did we do? Then we did the loop law. So that way we could find the total current going through. Well, we found the total current going through by using another equation, which was, if I can get this to move, maybe not. Okay. Which we had over here was that I equals the EMF plus the total resistance. So that is why it was helpful for us to find the equivalent resistance first. So if you have a question that tells you do this and then do this, that's often a hint that you're going to be using what you just found in the next part of your problem. So just keep that in mind as well. So we knew that our EMF, we knew what that was, and then we found the total amount of current flowing through our entire circuit. And then, if I can move this over, then we used that information and put that in the form of an equation down here of I1 plus I2 equals 2 amps. And then we found through using the loop law and the sum of the voltages in a closed loop being 0, we calculated the current through this equation, and then we manipulated it so that way we could plug in an I2 value that was equivalent to I1, since we wanted to know what was going on with I1 and flowing through this 5 ohm resistor, which it wouldn't matter if you called that one I2 and this one up here I1, as long as you were consistent with your calculations. And then we solved for I1 that way. And after we found the current that was specifically flowing through this 5 ohm resistor, we plugged it back in to find the power dissipated by this 5 ohm resistor. Okay, so sometimes it's helpful to kind of go back and say, okay, what did I just do? So that way your brain can kind of assimilate what just happened. Okay, so let's look at this next part, which we're going to need to move that down. Probably more than that. Yeah, we're going to need to move that down. Whoops. Okay, so this one says, apply Kirchhoff's laws to find the current through each resistor in the circuit. All right, so like with all the other ones, we're going to be redrawing our circuit every single time. And the very first, we'll go ahead and do that first. Now, with Kirchhoff's laws, you want to consider, we're going to use the guess method for this. And this is where we rewrite everything and you label what you have and what you don't have. Well, when someone says use, or a problem says use Kirchhoff's laws, you know that you're going to need to follow some steps. The first step is going to be label your current. Okay. After you label your current, then you're going to be able to identify your unknowns, which is the next part of our guess method. And this is important because you need to count your unknowns, because the number of unknowns that you have is going to need to equal the number of equations that you can come up with based on the loop laws. Oh, and that's messy. The loop laws and the junction rule. So we're using all Kirchhoff here. Okay, so let's go ahead and see what that would look like. So I'm going to start with current, let's say right here. All right, so I'm going to have my current start here, and it's going to go around, and then boom, it hits a junction. So we have a junction here and a junction here. Junction means my current has choices. So I have I1 going around this way. And it gets right here and decides that some of it is going to go this way, and that some of it is going to go this way. And I really could have started here. I'll start right here, so that way it's just covering the whole bit. All right. So we now have, this is I2, and this is I3. So now we have 3 unknowns. So let's put that down. We don't know I1, we don't know I2, and we don't know I3. But that's okay, because we have Kirchhoff's laws, and we're going to go ahead and use them to solve this. So let's see, we're going to get one of these equations from this loop, which we'll call loop 1, and we'll call this one loop 2, and then we can also get one from using the junction rule. So let's do the junction rule, because that one's easy. So the junction rule equation says that the sum of the currents entering a junction must equal the sum of the currents exiting a junction. So we have junction A, and the sum of the currents entering, that's going to be I1, equals the sum of the currents exiting, which is going to be what? I2 plus I3. Well, for junction B, we have the sum of the currents entering is I2 plus I3, and the sum of the currents exiting, well, that's just still I1. And you can see here that even though it looks like these are two equations, if it's not giving you any new information, it's not considered a new equation. So that's just one of our equations. Now we need 2 more. So we're going to use the loop law. All right, so let's start down here, since we started our current there. So we're going to go through this right here, and we see that our loop is pointing in the same direction as our current, so we're going to be subtracting the voltage here, which is going to be minus I1 times 4 ohms resistance. Keep going around. We come to the positive end of the battery. That means we subtract the voltage. We're going to be subtracting this voltage too, so let's just do that all in one swoop. Then we're going to come around here and you're going to hit this resistor, and it's going in the same direction. Our loop is going in the same direction as our current, so we're subtracting that too. Minus I1, 14 ohms. And then our I1 doesn't go in there, and it's just going to hit right here. This is how our loop is going. This loop isn't inside of here. It's only considering right here. So we're going to keep following around, and now our loop is still going in the same direction as our current, but now it's a different current. Now it's I2. And so we have subtract I2 times 9. And remember, the sum of the voltages in a closed loop equals 0. So let's put our things together that go together. So now we have our I1, and we have 4 and 14. That's going to give us 18. And then we have negative 24. You put those together, and we have minus I2, 9 equals 0. Okay, so this is also going to be an equation. That's an equation. And now we can look at the next loop. All right, so this loop right here, let's start right here. Doesn't matter where you start as long as you go along the whole loop. I'm going to go around and I'm going to come to this first resistor, R3, which has the current I3 going through it. And so we're going to say, since it's going in the same direction as our loop, we're going to subtract I3 of 18 ohms resistance. And then we're going to keep going around. And now our current I2 is flowing opposite direction of our loop. So we're going to add this one, which is I2 times 9 ohms resistance. And again, sum of the voltages equals 0. Okay, so now that we have our equations that we have found from doing this, okay, I needed to make a little bit more room. All right, so we're going to take the equations that we found from using the junction law and the loop law, and we're going to plug them into each other to solve for variables. Well, we've already solved for I1 using, I2 and I3. So let's plug 1 into equation 1. We'll call this equation 1. This will be equation 2, and this will be equation 3. Let's plug 1 into 3. Okay, so before we do that though, let's solve for I3 and see what we get. So I3, we're just rearranging equation number 1, is going to be I1 minus I2. So let's plug that in. So we have a negative I3, so that's going to be negative, well, let's bring the 18 out too. Negative 18 I1 minus I2 plus 9 I2 equals 0. All right, so we'll go ahead and we'll distribute here. That's going to give us a positive 18 I2 plus 9 I2, which is going to give us a positive 27 I2 and a negative 18 I1. So if we move I1 over to the other side, we'll have a positive 18 I1. And then we can divide by 27 to solve for I2. And so that's going to give us 2/3 I1 equals I2. And then we can plug this 2/3 I1 into equation number 2. for I2. So we'll have negative I1 18 minus 24 minus 9 times 2/3 I1 equals 0. And then when you distribute that, you get 18/3 I1, which we know 18 divided by 3 is 6, so we can just go ahead and put a 6 in here. Oops. 6I1 minus 24, and then we have still minus I1, 18. 18 and 6 is 24. So now we have negative 24I1 minus 24 equals 0. Let's bring 24I1 over, and then we have negative 24. And so when you divide this 24 away, you're going to get that I1 is equal to negative 1 amps. Well, now that we have that, we know that, where do we find it? Up here, that I2 is 2/3 of I1, so we can say I2 equals 2/3 of negative 1, which is going to be negative 2/3. So we'll just do this right here, amps. And then now that we have those, we can just plug those both into the very first equation that we solved for to solve for I3 right here. So we know that I3 equals I1, which is negative 1 minus negative 2/3, and that is going to be minus 1/3 amps. And for these problems, the biggest thing is to just keep practicing. Okay, so for this next problem, I accidentally erased half of it, so I rewrote it in here, so that's why you're seeing it looks a little different from this part. Okay, so the question says, the timing device in an automobile's intermittent wiper system is based on an RC time constant that utilizes a 0.5 microfarad capacitor and variable resistor. Over what range must R be made to achieve time constants from 2 to 15 seconds? I just forgot how to read for just a second. Okay, so we know that a time constant is tau. This is the Greek letter tau, and I was going to spell it and then just thought, maybe I don't know how to spell it. Maybe that's the Dow that I'm about to spell, so I'm not going to spell it. But it's called tau, and it equals RC, and it has a unit of seconds. All right, so this R is the resistor, and this is the capacitance, or I should say resistance and then capacitance. So what it would equal is the seconds. So we would have R1 C1 equals 2 seconds, and then we would also have 15 seconds equals R2 C2. Well, actually we don't need to say C2 or C1 because the only thing that's varying here is R. That's the only thing that's varying. So each one has a C of 0.5 microfarads, which is times 10 to the negative 6 farads. And so all we will be doing is solving for our variable, which in this case is just going to be the different R's. All right, so we do that by dividing away the 0.5 times 10 to the negative 6 for each one. I'm going to do the same over here. Okay, and then we will put this in our calculator and get our answer. So this one is 4 times 10 to the 6 ohms. If I counted those zeros, 1, 2, 3. Yep. Okay. And then for this one over here, R2, we get 3 times, I can put 3.0, times 10 to the, oops, oh, goodness, 10 to the 7 ohms. Okay, so what we need to do is we need to have a varying resistance from 4 times 10 to the negative 6 ohms to 3 times, goodness, 10 to the 7 ohms. All right, so then let's see what else we have. Okay, so it says a proton has a speed of 3 times 10 to the 6 meters per second in a direction perpendicular to a uniform magnetic field. And the proton moves in a circle of radius 0.2 meters. What is the magnitude of the magnetic field? Okay, so we know that we have a lot going on in this. We're given so much information in just, 2 little lines. So we're told, well, let's unpack this. Let's see what we're actually given here. So we're told that this is a proton. So we know that a proton has a mass, which you'll probably be given this if you're given this question. You'll be given like a constants list of 1.673 times 10 to the negative 27 kilograms. We're also given a velocity right here, speed, velocity of 3 times 10 to the 6 meters per second, and a direction perpendicular. And that's going to be important because when we're talking about the magnitude of a magnetic field, your magnetic field equation is going to include, like if you do sum of, let's see, it's going to be QVB is the force, but it's QVB sine theta. And this is the force due to a magnetic field. Well, if it's perpendicular, then this is going to be sine of 90, and that equals 1. So that essentially just goes away. So when you're given things like that, pay attention to all these little key things. So we're given that, our direction is sine of 90, so our theta is 90 degrees. And then, let's see, and then it says that we're moving in a circular radius, so our radius is 0.2 meters. And so we want to know this, the magnetic field magnitude. So some equations that we have for this is going to be, we know that from Newton's second law that the sum of the forces equals mass times acceleration. But here we have, if you remember from your 201 class, or whatever it was called, the class before this part of physics, then you'll know that for an object in circular motion, you're going to have mass times centripetal acceleration, which is v squared over r. Well, we also know here that we're talking about the sum of the magnetic force, right, which we just said was QVB sine of theta, but it's sine of 90, like we said, so that's going to equal 1, so we can just leave that out. Well, since these both equal, the sum of the forces, that means that we can make them equal to each other. So we can say QVB equals mv squared over r. Okay, well, what are we solving for? We need to solve for our unknown, which is b. So we just need to rearrange this equation, which we'll do in substitute. And so we'll solve it for b. So we have b equals mv squared over QVR. Well, one of those v's is going to cancel, so then we have mv over QR. So we know our mass, the mass of our proton, is 1.672 times 10 to the negative 27 kilograms times our velocity, which is 3 times 10 to the 6 meters per second, divided by Q. Well, the charge of a proton is the same as, but positive, as the charge for an electron, which is 1.602 times 10 to the negative 19 coulombs. And you'll probably also be given that, but eventually you do it so much you start to remember it. And then R here is a circle of radius 0.2 meters. All right, so then we're going to put that in our calculator. Okay, and we get that the magnitude of our magnetic field is 0.156, so we'll say 0.157 Teslas. Which technically we were only given 2 significant figures here for each thing, so we could say 0.16 Teslas. Unless I counted something. No, that should be correct. Yeah. Okay, so 0.16 Teslas. All right, now for number 8. We're almost there. A long wire carrying a 2 amp current is placed along the y-axis. What is the magnitude of the magnetic field at a point 0.6 meters along the x-axis? So when you have a problem like this, draw a picture. If you're not given a picture, draw a picture, because if you can't see the problem, you can't solve the problem. So here we go. We have a wire. He's hanging out on the y-axis, okay? And he has a magnetic field around him. But we want to know, what is the magnetic field 0.6 meters along the x-axis? So we know that a magnetic field equals mu naught, which is just a constant, times the value of the current divided by 2 pi r. Well, what is mu naught? Mu naught is 4 pi times 10 to the minus 7. And this is one of the reasons why you need to practice with your calculator. I was doing this problem, or another problem, and I put this 4 pi times 10 to the minus 7 in my calculator, but I did 4 pi e to the minus 7 because I do that a lot, and I usually don't have any problems. And I put this in, and it kept making my answer 4 pi times 10 to the minus 6 and completely screwed up my answer. And so make sure you're practicing with your calculator so you can avoid surprises like that. Okay, and so our current is 2 amps. And then we are dividing by 2 pi, and then our radius, right, is going to be right here. It's going to be 0.6 meters. Now, one thing that's also helpful to see, if you don't see it, that's fine. Just put it in your calculator, practice putting it in your calculator, but these pi's cancel. And so that's going to make putting this in our calculator even easier. And I'm always recommending that calculator life be made as simple as possible. Okay, so let's put this in. Okay, so I get that this equals 6.67, which really we only have, again, 2 significant figures here. So we could just say 6.7 times 10 to the minus 7, and that's in Teslas. Okay. Now, here we go. 2 long parallel wires carry currents of 5 amps and 8 amps in the opposite direction. The wires are separated by 0.3 meters. Find the magnetic force per unit length between the 2 wires. Okay. So I'm grabbing my equation sheet, and I see, well, we'll go ahead and we'll draw a picture real quick. It doesn't have a picture. You don't really need a picture for this one, but, you know, if you like to see what's going on. So we have 5 amps of current going, you know, we'll say that one's going this way. Well, we know this one's going the opposite way. Say this is the 8 amps. And they're separated by 0.3 meters. And we want to find the magnetic force per unit length, because as you can see, we aren't given the length of the wire. So we just want to know what's going on per unit length. Okay, so here we go here. I have found that this equation works every time so far for force per unit length with 2 wires. And it is this equation. Force per length, which you're not going to be doing anything with that length except for keeping that in your answer as newtons per meter, equals mu naught times current 1 times current 2 divided by 2 pi d, or 2 pi r. It would be the same thing. So normally the wires that are carrying current, we would say force net. If you're given the length, you would say mu naught 2 pi times I1 times I2 times d times length. But since we don't have length here, they just said, hey, let's call this force per unit length, and they just divided that guy away. So that's what happened. But this is another equation that you could use if you were given the length. Okay, spiel, just a little side note. So all we need to do here is fill in what we have. So we have mu naught, which is, again, just a constant, which somehow I just forgot. Okay, 4 pi times 10 to the minus 7. And then we have I1, which we'll just call 5 amps. And then I2, we'll call 8 amps. Divided by 2 pi, and the distance between them is 0.3 meters. All right. Let's put this in the calculator. And I get 2.7 times 10 to the minus 5 Newton meters is going to be the force per unit length between the 2 wires. Okay, so as you saw just before, this question was erased a little bit, so I just went ahead and rewrote it. And so it says a solenoid of 200 turns carrying a current of 2 amps has a length of 25 centimeters. What is the magnitude of the magnetic field at the center of the solenoid? So the equation that we use for the magnetic field of a solenoid is mu naught times the number of turns times the current divided by the length of the solenoid. Okay, and so we're just going to fill this in. So this is 4 pi times 10 to the minus 7. The number of turns was 200. And the current is 2 amps divided by the length of 0.25 meters. That's just the 25 centimeters converted to meters. If you're not comfortable with that, you can always divide by 25 times 10 to the minus 2 meters if you're not comfortable with converting on your own yet. Okay, so then let's put this in our calculator. Okay, and we're just going to say 0.002 Teslas. And since this is technically just one significant figure, let me see how the problem actually gave it to us. Yep, it was just one significant figure, just the 2. So 0.002 Teslas is our answer. All right, I hope that this was helpful.